presentation is going to be looking at utilising the new interfaces, I guess, add-on or feature, I guess, really for LabVIEW 2020, specifically aimed towards looking at hardware abstraction layers. There's going to be a slight addition of measurement abstraction as well, because I think it relates quite nicely. You'll have seen on the initial sort of invite and the post on the forum post that there's a couple of videos, documents that I think would be beneficial to go through and have a look at, specifically from NI themselves. So hopefully you're at least aware of those videos. If you're new to sort of object-oriented principles and or interfaces, I highly recommend that you view those before. This will be recorded, so I think it's probably best if you go through those, come back and then watch this. But hopefully I'll keep it as easy to explain as possible so people can pick it up. I'm not going to go too in depth into specifically hardware abstraction and interfaces of what they are and why they're useful. It's going to be more aimed towards specifically applying them both together in a I guess a real world application. So we'll begin. I'll be referencing some documents and some images as we go along. There's some QR codes at the top of some of the slides as well. So feel free to grab a picture of those, and I'll share the links of everything that I've referenced as well, or things that I've used, because there's a lot of really good information about both interfaces and hardware abstraction out there. A lot of it geared towards LabVIEW, a lot of it sort of external to LabVIEW. So it's been a bit of a lifesaver over the last few years since I've been looking at hardware abstraction. So, okay, so I guess first of all, what we'll do is we'll just do a bit of an intro to myself, really. So I'm Jonathan Hobson. You've probably seen Herd as a surname on some of the invites. That was my name before I got married. For some reason, our email server keeps Herd on for some reason. But anyway, so I'm based at an alliance partner, TBG Solutions in the UK. I've been there for about 5 years now. I'm looking after the systems engineering team for around 3 years this year. And that's primarily a team of software engineers, but there are a number of electrical and mechanical design engineers. Crux of what we do really is mainly automated test, but harness build. It could be simple rack, it could be a full turnkey solution, the whole range of anything and everything. I used to work at NI as an intern as part of my degree at university, electrical electronic engineering. I spent just over a year there. And that's really where I got my teeth stuck into LabVIEW, and then ended up working at TBG from that. In terms of projects that I've worked on personally, I mean, it's a whole range of different applications. A lot of stuff with the Joint Strike Fighter program, renewable energy wind turbine blade test, a lot of high channel count, strain measurements going on there, a lot of aircraft engine test, various components to full sort of, I guess, end of line or in service test. And then end-of-line commercial PCB testing, so a whole range and varying different applications. And to be honest, all of those are very much different aspects and different industries and different applications, but all come back to, I guess, the core of the systems that they run on. You know, really, hardware abstraction is a key part of that. Did a presentation last year at HIWeek, which really sort of pinned down more of what is hardware abstraction and why you should be doing it. I believe that I also presented that at GDevCon number 2 as well, so that should be recorded and on YouTube somewhere. So that's again another good presentation where it sort of sells the abstraction, hardware abstraction ethos really, and why it's beneficial. Very quickly, I've already mentioned what TBG do. We're a Gold Alliance partner in the UK, been around for 19 years this year. We're a small team, but every time I put this slide up, we get bigger and bigger. So we're about 45 engineers, 2 different sites, one in Scotland and one in Chesterfield in the north of England. And yeah, like I say, software, hardware, harness, AT, pretty much anything and everything we will do. Some examples of some of the projects, and again, where hardware abstraction is at the heart of the application. So we've got an underwater ROV with a LabVIEW interface with lots of fancy ActiveX controls on the front. this was really sort of the first application of where our sort of, I guess, version 2 of hardware abstraction sort of got put in place. So we've got a number of different hardware elements there. We've got barometers, we've got temperature sensors, a whole compact Rio system, a lot of stuff going on. Other spectrum to that, a pure benchtop data acquisition system for wind turbine testing, looking at the actual nacelle that sits on the back of the wind turbine. So we've got I think a 6 or an 8 megawatt permanent magnet motor, a force actuated system to simulate stresses and strains of wind blowing on the blades, and then the actual unit under test that's attached to some very expensive concrete piles, foundations. So again, 13, 14, possibly even 15, depending on what they're testing, different box or rack instruments that need to be combined together into one or multiple applications. And again, hardware abstraction at the heart of that. And then lastly, sort of an example of a traditional rack build that we would do. This is for testing 3 avionics PCBs in parallel. So there's a large PXI, 18-slot PXI chassis in there with some Pickering switching and things like that. And again, box instruments, PSUs, AC and DC loads, switch cards, switch chassis, amplifiers, all under a hardware abstraction layer. And it's the core of what we do, really. We think more I've thought about it, the more it is at the core of pretty much everything we do. It's pretty important. So I guess a agenda of what we're going to go through. I'll give a bit of an intro to hardware abstraction for those that aren't aware. It'll be very, very top level. It won't be too in depth. Again, I would recommend looking at the presentation that I did at NIWeek and GDevCon. I've got a couple of slides on interfaces specifically. Again, I think I'm not going to explain interfaces half as well as Stephen Loftus-Mercer and all the guys in NIR&D. And Stephen's done a really good presentation and a couple of times now at CLA Summits on interfaces. And I've linked those slides and those videos in. I highly recommend you go through those if you want a bit more of an in-depth look at interfaces. There is also a decisions behind design document specifically for interfaces. I know there's one for object-oriented. Again, there is one for, here we go, decisions behind the design. So I highly recommend you look through this. It goes a bit more in the back end of naming conventions and sort of form and function. Then we'll look at, again, I've not got a specific slide, but it's more a case of there's a couple of slides that I'll talk around why HALs and interfaces are, I think, in my opinion, a good fit, a good match together. We'll look at some example code. I've got one example of, I guess, pure hardware abstraction, and then I've got a LabVIEW test and example of hardware and measurement abstraction. And then, we'll hopefully have some time for questions. So hopefully it'll all make sense. And like I say, if there are any questions, just feel free to pop them in the chat, or if you want to wait till afterwards or a bit more in-depth discussion, I will be around. There's nothing else to do at the minute, right? Just sitting around at home. So, okay, so hardware abstraction. So you're going to see a lot of these blue images. These are going to be taken from, in my opinion, probably one of the best white papers that's ever been put together from a National Instruments perspective in terms of technical content. So it's sort of a NI and partner white paper. Bloomy Controls is the partner, Grant Gothin specifically, from their R&D department. It's called Fundamentals of Building a Test System, Hardware and Measurement Abstraction Layer. I found this about two and a bit years ago, where I was starting to look at what measurement abstraction was, and didn't really make sense to me. And as it turned out, after reading this document, hardware abstraction didn't really mean a lot to me at that time either. But yeah, if you get a chance to have a look through it, I have linked them both up here in the QR. Well, I've linked this one here in the QR code up here. On a more general term, object-oriented, I think one of the best presentations I've seen is from Dan Harriman, looking at encapsulation and object-oriented programming, and that was at GDevCon #1, which seems like a lifetime ago now. But that hardware abstraction, measurement abstraction document, It's pretty comprehensive. It's 30 odd pages long and goes through a whole range of different sort of real world applications. It gives examples of when to use things, when not to use them, and also gives a good sort of base foundation to build upon. So you're going to see a lot of these. Well, I'd say two or three really. So the example that you got there is what if we've not got any kind of abstraction. So we've got a test sequencer that calls some code modules that calls some instruments. Going back to the adage of the everything all in one bad VI, the spaghetti code example where you've got this code needs this code to run, and if it breaks, it breaks. You've got a number of things to think about. So the biggest one that I find with customers of mine and TBG's, I guess really in the aerospace defense sector mainly, is instrument obsolescence. So what if NI or Pickering or Keysight pull support for a card that you've got in 50 pieces of test kit? What do we do with that? How do we refactor the code? How do we future-proof it? How do we approach new test systems? That's a real big driver, and that's one of the big things why we've pushed our hardware and measurement abstraction on. What if the test process changes? If you've got everything all in one VI, again, how are you going to refactor the code easily? How are you going to, make sure that you can run n number of different product variants? And also, if you need to reuse the code, what are you going to do? Are you going to take the whole complicated VI and try and pick it apart? No, you're going to create yourself a bit of a rod for your own back. So that's sort of the example of no abstraction. So this sort of gives a better, I guess, context of what I'm talking about with, say, if a card needs swapping out. So you can see on this slide here, we've got a simple process or a simple occurrence of a card needs to be swapped out for one reason or another, either a process change or the card's obsolete. So just changing that one card with that bad code, we've got five things that we need to do. So we change the instrument physically. We change the driver layer, which is within that big code module VI. We've then got to make sure that the code module call, if there's an input or an output in test stand that's different, we need to make sure that that's being updated properly. The function call might need to be changed as well. And then the whole test sequence might need to be updated. So there's five key things there that are going to have to happen, which if you've got this code reused in multiple places or that card used in multiple places, you're going to have to repeat that over and over and over again, which Control F could only get you so far with certain things. But you can see sort of how we're sort of blocking ourselves off there. And again, like I say, rinse and repeat for all uses. Where we start to get into more of an abstracted hardware layer really is where we're looking at leveraging the object-oriented principles, things like class hierarchy, things like dynamic dispatch, inheritance, whereby we're not clumping everything all in one VI. We're modularizing the code. We're breaking it out into, okay, so this is dedicated for a power supply. This is dedicated for a DMM. And then inheritance-wise, we then have child classes that inherit from the parent, DMM or PSU. So that could be individual driver, individual drivers like DACMX or NIDMM, or if you go into the more complex side of HAL MAL, you might be looking at abstracting individual card types. So not every DMM is the same as the other, and so on and so forth. But you can see here we've got a bit more of an abstracted test methodology, I guess, really. We've got the high-level code modules, which have been then we've got our instrument drivers, which have been called by the high-level code modules, and then we've got the actual instruments themselves. So you'll see we've got some NI equipment, and then we've got an XG, which I think is like an Amatec power supply. So if we think about how we're implementing this, it's a much more modular approach. So say if the PSU needs to be swapped out, we just define what PSU we need to be called in one step rather than changing 5 different things. again, as you get more into the measurement abstraction, you start to look at things that I'll talk about in a second, like mapping frameworks and things like that. But abstracted in this way means that, we've got individual code modules for individual parts, and basically the class that we're telling it to dynamically dispatch from is really the only thing that we need to change, whether that's done from disk or whether that's done from a constant VI. So again, a simplified example. So we've got two, code modules here. We've got a test interface code module, and we've got a debug interface code module. Both of those are calling n number of drivers, which are then calling n number of items of hardware. So say, for example, we've got a DMM. All we're doing in principle by changing the class that we're calling through dynamic dispatch is we're essentially swapping DMM1 for DMM2. Okay. Someone scared me in the chat. Okay, cool. So we're essentially swapping the DMM1 for DMM2. And that's essentially what we're doing with the dynamic dispatching in principle. So all we're changing is where or what we're calling. So this is slightly wrong. The transition has not happened. So what I will do is I will just move that to there. And from this slide. Okay, so looking at taking that a step further into a measurement abstraction, this will become more apparent later on. So we've got sort of our step types. So this is sort of a level higher in that we need to do some kind of switching, some outputting, some inputting, applying power, for example. And then we've also got our hardware abstraction that we've just spoken about, where we've got multiple drivers, multiple hardware. How does the hardware relate to the measurement? What do we need to do for a signal output? Is there a specific card that we need to use? And for that, we use something called a mapping framework. Now, typically, that could be something like a .ini, a configuration file. I've seen it before where people have saved it as class data, as XML. It's really, really personal preference. So in terms of how that looks in how we approach the test itself would be something like this. So in the test sequence, we've got a step where we need to measure a 5-volt rail. So we have basically the measurement abstraction where we know that the signal input, that we're calling, is going to be a case of connecting a 5-volt rail, measuring a 5-volt rail, and then disconnecting the 5-volt rail. But what hardware are we using for that? That's where the mapping framework and the configuration file comes in. So you can see down at the bottom, the configuration file that we've got saved. It has an entry within it that's called 5-volt rail. That's basically all the information related to anything with the 5-volt rail. So there are some connections with a PXI MUX card, and there's some measurements with an NIDMM card as well. So it's got the acquisition type, DC volts in this case. It's also got the MUX or relay channel 7 that we need to connect. So the mapping framework would be a VI call or something that basically says, okay, well, we need to connect. So pull in the settings, connect channel 7. Okay, now we need to measure DC volts on this card, and then disconnect channel 7 from that same card. So in terms of relating to the hardware abstraction, it then knows that it could be based upon alias. It could be part number, probably not serial number, but we're then going to be calling the correct hardware abstraction driver. So in this case, NI switch for the MUX and NI DMM for the DMM. And then that's going to be obviously via the PXI backplane, whatever, talking to the card, getting the values back, and then back up the value to the test sequence pass fail. Okay. So again, this is going a level even higher in terms of we're abstracting the measurement as well as the hardware itself. So we're taking it to the next level. it is a game changer in my opinion, because now you can create things. You can create test sequence templates whereby you can have 50 different ways of, or 50 different things to test, and you can test it largely in the same way. It might be a complete different product variant, but the bare bones and principle of how you're looking to test really is based around the mapping framework. Defining what is the 5-volt rail, for example, or what is a voltage measurement, what is a current measurement, what instruments need to be used. We've used this type of abstraction combination for an end-of-line PCB test system, whereby there was 150 different product variants, basically dynamic test sequence calling to be able to call a specific product variant that's got obviously different mappings of pins and different switching methods that need to happen. And basically they all run the same template frame, test sequence framework, but they do massively different things. So let's move on to interfaces. So again, if you've not seen the presentation by Alan and Stephen that was given, I think maybe 2 weeks ago now, I recommend that you go and watch that. And I also recommend you have a flick through this document just to give you a bit more of a background information. So interfaces. So I guess really people that have been programming in other languages are probably, or specifically object-oriented, are probably familiar with what interfaces are. From a LabVIEW perspective, we're really, it's going to be it's here already, but it's really a game changer in terms of how we can approach specific problems, or I guess really different use cases that you might have been sort of jerry-rigging your way around, making your own VIs to serve the function of what an interface can do. So within a lot of these presentations and a lot of the documentation, loosely describing an interface as a class but without private data, and I think that's true, but in my opinion, it's separate to a class. It serves a different purpose to a class. There are some carryovers, some crossover in terms of inheritance and things like that. But the key thing to remember, and this is the one thing, because I approach interfaces from not looking at maybe text-based programming languages, looking at from a pure LabVIEW perspective. I didn't really grasp the fact until looking at the design documents and things like that what we're doing with interfaces is we're defining the capability or the function. We're not defining what data needs to be used. I've got a slide in one slide's time that visualizes that a lot better than I could ever explain it. But yeah, it makes things really, really flexible and very powerful in terms of, especially from a hardware abstraction perspective. There are a lot of other active framework use cases like abstracted messaging, things like that, mock testing, which I don't know if Sam Taggart's going to go into anything with interfaces on mock testing, but it's certainly something that it could be a use case for. So the big thing for me in terms of how this links into the hardware abstraction is that because we've got no private data, or I guess related to the fact that we've got no private data, we can have multiple inheritance, you could call it really. You'll see in some of the class hierarchies that I put together what I'm meaning by that, and how that differs from how we probably looked at doing it before. One thing to note is that it's got a visual difference from a class in terms of its icon. It does share the .lv class extension, but that's pretty much as far as it goes in terms of being similar. In terms of setting up, as you'll see in one of my examples, Sam says, that is on my radar, but my toolkit is in 2019. Okay, so he's not going to go into that, but it's on his radar. Maybe this will whet his appetite to get into it. But really, yeah, so like I say, we're allowing multiple inheritance. It's really allowing us to be a lot more flexible and more powerful with object-oriented in general. I'm seeing it as really an extension of OOP capability. I might be wrong in saying this, but it's not a case of using interfaces instead of classes. It's a case of using them together. And initially I was skeptical of my personal use case, but sort of going through documentation and asking questions, really, it's sort of really hit home that actually there are benefits to using pure abstract classes, but this allows you to go sort of the next level up, and hopefully you'll be able to see that. But I'm not going to explain that anymore. Stephen and Alan give a much better explanation than me. Okay. Oh, wow. Okay. So the man himself, Stephen, says interfaces are useless without classes. One augments the other. So, yeah. If there's anything clear that needs to be added than that, I don't think there is. So we shall move on. So this is the image. Now, this is obviously not pertinent to LabVIEW specifically, but this, as someone who likes visual things, this sort of explained things to me in a way that made sense. So I've got a concrete class and a subclass, normal, I guess sub VI if you like. We're extending the capability through an override, maybe not a sub VI. Abstract classes, we're defining a method, and the subclass is allowing us to get an extension of capability. With an interface, again, what we're doing is we're not defining the function. We're not defining the data, we're defining the function. So it's a case of anything that inherits from that interface has to override it. So the subclass is implementing that function in its own way. And you can imagine, as you'll see later on, NIDMM voltage input is not going to be implemented the same as NI-DACMX voltage input. For one, it uses a completely different driver layer, but also the configuration is going to be different. And that's one of the really powerful ways that I think interfaces can be used in HAL. That was from a Stack Overflow image, so I don't know. Yeah, a bit skeptical. Okay, so how would we use a HAL using normal loop? So we'll go back to, I guess, one of the slides that I've put earlier on and give some context to some benefits and drawbacks. This is where we're going to be looking at the specific use case for HAL and interfaces. So we've got some benefits here in general. I guess really, if we take a step back really and look at what we've got. So we've got we've got 4 instrument types inheriting directly from LabVIEW object. Some would argue you may well want an instrument parent that's above that, sort of inherits as sort of a grandfather class. I've used it with and without for different use cases, but we'll go with the simple option here. And then obviously we're inheriting n number of instruments. Now these would obviously be individual. It was just easier to draw a rectangle than it was 50 million squares. So some benefits of that is we've got clear inheritance. We can see exactly that, the PXI 4081 inherits from DMM. We can see that PXI 6225 inherits from MIO. It's dynamic. It leverages OOP. It's dynamic dispatch. We can reconfigure it very easily. It's modular, and it works. It does work. However, drawbacks, in my opinion, again, is that in a way we've got single inheritance, and when you're opening yourself up to lots of classes for classes' sake, that's how I would describe it. And you'll see that when we're looking at specifically the AC source, also really applicable to SMU and DMM. So SMU is source measurement unit for sourcing current and voltage. MIO, mixed input output cards, so things like a 6225, which can do analog, digital, anything and everything. There are a lot of similarities between, for example, an SMU and a DMM. There's also similarities between a DMM and an MIO card. Both of them can read a voltage input, right? Same for an SMU, in fact. Some would argue that an AC source could read a voltage through a query, but I would steer away from that. But as you'll see later on in some further examples I've got, an AC source could be seen as something like a signal generator. An AC source is generating an AC sine wave. You can generate a sine wave from a function generator, right? There's some similarity. So there's a lot of common features that I think are shared between that this sort of hierarchy, in my opinion, doesn't really allow for utilization. and interfaces can really help with that in what I've tried to put together. So here we've got an example that uses interfaces, and I'm going to load this code up and show you the class hierarchy again, and I've got a sample VI. You'll see some similarities, I guess, really with some other posts that have been put out there. So there's a really good blog post by the Boring Engineer. I'll make sure I put a link to that in. And that's a real good one in specifically looking at a DMM example using interfaces. There's also a YouTube video by Tom McQuillan that looks at the hardware abstraction more towards the measurement abstraction side of things, and that's my initial thoughts anyway. But yeah, this is sort of the example hierarchy that I've put together, in that we're still inheriting a parent from LabVIEW object, but we're not inheriting a class, we're inheriting an interface. And the reason we can see that, if you go through the documentation and links that I've provided, we can visually see the difference in that we've just got the top banner, if you like, of the icon rather than the whole square. There's no icons on these because there's no code. So yeah, you can see we've got DMM, MIO, and then what I've got here, well, I'll come back to that one, MIO, DCPSU, and then waveform gem. So what we've got here is we've got a level of abstraction down to a card level or an instrument level. But what we're doing is we're leveraging some of the common features that are between some of the instruments. Specifically, looking towards the CPX PSU, that's just a power supply type that I happen to have got on my desk. We've got a stereo and AC source, which again is on my desk. We've got a 41620, which is a Pickering voltage amplifier, signal generator FGen card that fits into a PXI. So again, as I was talking about earlier, we've got some commonality between really all three of them. So looking from a waveform gen perspective, a 41620 can output sine, square, triangle, waveform. So can the Asterion AC source, albeit through a different driver layer and albeit through different voltage levels. I think it's capable of like 500 volts, whereas the 41620 is 0 to 10 volt. CPX PSU, that just outputs voltage with a current level. But the AC source can also output a DC voltage as well. In theory, the 41620 could, I think, but specifically the AC source, I know it can because I've written some code for that. So actually what we're doing is we're inheriting components of the DC PSU and waveform gen into all three of these instruments. Okay, sort of going back to more towards CPX can be. So I've got a question saying CPX can be a DMM as well. Why not in this example? I guess sort of in CPX could be it could be seen as a DMM in theory. I would personally stay away because it's more of a query than it is actually a physical read, but some would argue that it's still a voltage read. So you could be quite right in that would be applicable. Personally, I would, if I was going more towards measurement abstraction, I think I have actually done it. I have allowed it to inherit from a voltage input type. But yeah. So MIO and DMM, you can see we've got instruments, and I put those. Yeah. So Tim Robinson said most power supplies are horrible at being a DMM. Keep that for SMUs. Yes, that's a good note actually, and that's sort of something that I alluded to in this slide here. And in fact, the Boring Engineer post specifically looks at combining the capabilities of inheriting DMM and voltage output between a DMM and an SMU. So I've got these two, the MIO and the DMM here, really just to show, as you'll see in the code, sort of how we're still leveraging dynamic dispatch. We've got devices that share the same driver layer, both PXI, DACABEX cards. DMM wise, we've got a Keithley 2200 series, which is a benchtop DMM that is not going to be using NIDMM. So just to show that we can still use in conjunction with interfaces the dynamic dispatch capability. So some benefits. Again, we've got clear inheritance between interfaces and instruments. That's a bit more clear with the MAL stuff that I'll show you, stuff that I've implemented before, where you don't know what's going where. In my opinion, we've simplified the HAL because we're not having to create a separate. We're not having to create a separate AC source, parent class. We're just inheriting directly from the interface itself. Now, some may argue that you may well want an abstract class that sort of is an AC source. That's fine for me. That's just an extra layer that you don't need, because you're just going to be, what functions are you going to be serving in that? I don't know. We're defining the operation, not the data. It also is the beginnings, I guess, of solid implementation. So Peter did a really good presentation. I think he's got the slides on LinkedIn, actually, and obviously it's being recorded for VIWeek from 18th of this month. And again, it works. So we'll have a look at the code. We'll hope that it does work, because it worked about 15 minutes before this. So, a quick side note as well. Can we all see LabVIEW? Can we all see? Anyone? Yeah, cool. Thanks, Neil. Okay. Yeah, quick note on the LabVIEW fundamentals in the LabVIEW help. It's got a lot of really good information specifically about interfaces, and it relates to the shipping example as well. That's why this is called no pry tool needed at the end in brackets, because the example is all about prying tools. Bad use of comedy. But yeah, some really good information on there. Shows the hierarchy in more visual terms, so I'd recommend you have a look through that. And a lot of documentation in that LabVIEW fundamentals is really useful. I certainly learned stuff from looking at it the other day. That's for later on. That's test stand. Don't worry about test stand right now. So here we go. So interface HAL. So if we look at the class hierarchy, you will see this is what we've had on the last screen. So you can see we've got the inheritance. So what we've got is we've got a test VI. I've got some disable structures just so I can run one thing at once, and we'll eventually run it all together. But I just want to just break it out into, there's some key points that I just want to point out, that things do look different, things do change. So I'm not going to go into any slides are not changing. Oh, okay. We can all see the block diagram, right? Someone's saying they're not changing. Just help from NI. Yeah? Okay, cool. I'll carry on anyway. It will be recorded, so. Okay. The presentations given by Stephen and documentation and the actual shipping example go into a lot more depth in terms of how icons change and how we should be using to more dynamic or more specific classes, things like that. In the MAL example that I've got, you'll see that there's some caveats with using them. So what we've got down at the bottom is we've got the two DMMs that we've got, again, using different driver layers. We've got the Keithley and the PXI. We've got two sets of array of settings and aliases, so just to give some connection information. And then also to define what we're doing for the DMM settings, so whether it wants to be AC volts or DC volts, for example. Excuse me. We're then doing a read, and then we're closing the session. So what we will see is this is actually the DMM parent. This is the DMM interface. So yeah, I guess you could see it as parent, but you'll see that there's no code there. There's no code behind the scenes, because what we're actually doing is, like I've said before, is we're only defining the operation or the method. We're not actually defining the data or what goes on. That's not to say that these interface VIs can't have code within them. You'll see in the shipping example there is some code within that. Control and scroll. Okay. Anyway, so you'll see for the Keithley, what we've got is we've just got a VI that's just going to be reporting the class status. You'll see I'm utilizing the actually I'll show you actually. We're going to be using the debug.vim, right? If you don't know about this VI that is in Hidden Gems for VILib, learn about it. I always say this to everyone. I went on site to Indonesia in end of 2017, and that VI single-handedly saved me like 2 weeks of on-site time just from debugging with a customer system that didn't have LabVIEW itself. So, yeah, I'll always be thankful to Darren Messenger for that. So, okay, anyway, back to the code. So we're going to be opening, configuring, reading, and closing. What we've actually got for the PXI is we've actually got some actual PXI NIDMM code, which, because we've just got LabVIEW 2020, the driver layer got the driver sets were released as well. So I quickly rushed to change the demos, and they all broke, and they didn't. So yeah, what you'll see is we've got this wire here, which is the interface wire class. Oh, so shouldn't say class. It's the interface wire coloring, I guess really you could call it. Giving it some funky colors, green and red, so you can see that we're not calling a DMM class. We're not calling the Keithley class. It is the interface, and then we're going to be inheriting and dynamically dispatching from there. So if we run that, we're going to get a pop-up that's going to be showing. There we go. It's quick as that. Should have highlight execution on so you can see it a bit more. But what we've done is we've ended up with 2 DMM readings, and we've done all the DACMX stuff with no error, and we've done the Keithley benchtop stuff. Obviously, I haven't got the 20 version of that driver, and I haven't actually got that DMM on my desk. But you can see we defined the sessions opened. This is actually taking the class name that we've called or that's overridden the interface, and then the function that is provided. So you can see we've configured and then closed. So that's really showing two similar types of class that share an interface, a general interface. If we take a look at what should we look at next? Yeah, we'll look at this top one. So again, this is basically an example of sharing the same driver layer. Fab says, what was Zoom program? Okay. Some of you might be struggling with the Zoom, but anyway. Okay. So Stephen says, I have been using the term object wire, which covers both class and interface. I hadn't intended to use the term. But it's been useful for live sessions. Yeah, so I think object wire is probably the best way to describe it, rather than class wire or interface wire. I don't want to offend anyone. Okay, so yeah, so that first example was again showing the fact that we are overriding individual cards. Again, there's 2 separate driver layers going on there. This is an example of the same driver layer, NIDACMX. Again, you'll see we've got different sort of functionality in terms of MIO. So we've got a create voltage input task. So we're calling some DACMX code, carrying the task through in the private data of both cards, starting the acquisition, reading a double, and then closing. So trying to keep it quite modular and generic, really. So again, what we'll do is we've got broken run arrow. Oh no. There we go. It's always the simple stuff, right? So what we'll do is we'll go through, we will, right click menu is going to crash it now, isn't it? So what we'll do is we'll pro. So what you can see when we run this is that we have got the disable structures. So we've got a 6221 class coming in, and then what we've actually got is an array of the classes that are overriding the interface. Although you'll see that it is the object wire performing the creation, the start, the read, and then the close. And then we've got the MIO readings there. Okay, so that's showing similar drivers. Again, sort of the same in principle as the one down here. But I thought it was just good to show the fact that we are still leveraging the principles of dynamically dispatching different instruments to do similar functions. So this example here, this is where we're sort of taking it to the next level, in my opinion. So if we look at AC source and highlight the connections, so again, it's inheriting some interfaces it's inheriting DCPSU and waveform gen, and we look at the 41620, that's inheriting some of the waveform gen, it's overriding all the functions. Sometimes elevation just. Okay, there's some questions I will come back to. I'm conscious of time, people's schedules. So what we're actually doing is we've got two very, very different instruments here. One that's on the bench, one that's in a PXI rack, one that is an AC source, one that is a function generator, but they are sharing a lot of the same functionality. So again, you'll see we're leveraging the interface overrides. They both need to be opened in some way. Again, you'll see I've used the debug VI reporting class status VI that I've made just to show the functionality that's going on. They both need to be opened. They both need to be closed. They're both capable of setting sine, waveform, sawtooth. They both need a frequency because the function generators, right? Same for an amplitude. They've both got relays internally for the output being on or off. And again, they both need to be closed. So again, we're going to be we're all sorry, the chat has distracted me. So enable, there we go. Thanks, whoever that was. So yeah, they're both sharing a lot of the same functions, so they're going to be sharing the same overrides. So what we'll do is we'll run it. You'll see, I'll run it with highlight execution just so we can see.
Hey, Jonathan.
Yeah.
If you'd like, I can keep an eye on the chat and just break in when there's a question for you specifically that isn't something side chatter.
That'd be amazing. Thank you very much.
Sure.
So you can see we're going through the first instrument. We're actually going through the second instrument now. And what you'll see, again, we're leveraging interfaces to be able to override to a specific instrument's function. So we've opened the session on the PXI 1 slot 2. We've performed all the PXI function generator functions, setting square wave, frequency, amplitude, setting the output true, then false. Maybe we do some other measurements asynchronously elsewhere. And then next slot round, we've got a benchtop instrument, the Asterion power supply that runs through LXI. So again, we're opening the session through its device connection information. We're then again setting the waveform type, the amplitude, frequency, so on and so forth. But again, we're still calling the same interface, the waveform gen interface, but we're overriding to a specific use case. And that's where things start to become really powerful with interfaces. If I would never ever be able to do anything like this, really, in principle, with from a pure hardware abstraction viewpoint, with no interfaces, really, because we'd have to create a separate class for an AC source, a separate class for a function generator, and the inheritance. It could be, it could be a bit messy. Okay, so that's, I guess, really a simple example of multiple instruments, multiple driver layers being used in different ways, but sharing the same, I guess, inheritance from the interface itself. So you can see in terms of layout what we've got. Go back to the project. So you can see we've got the individual classes. So I've just grouped them nicely. So they're in there. And then interface-wise, MIO, DMM, waveform gen. So again, if we look at configure for MIO, you can see all the VIs that we're overriding. They're in the top there as well. Okay. So we shall save that.
Jonathan, I actually have a question for you. Mm-hmm. You've built this first HAL project using interfaces. Can you give some comment to folks about how well or poorly the user interface is behaving of LabVIEW, as far as, are there tools that you're finding yourself wanting, or things in the right places?
From configuring interfaces? Yeah,
and just generally usability.
Personally, I think it's pretty smooth. So when you're creating a class or an interface, this is sort of the similar sort of layout as what you'll see here. This window, if I'm right in thinking, it is new for 2020. Didn't see it in 19, correct?
Correct.
Yeah. So yeah, this sort of level of being able to create classes and interfaces is pretty sweet. The thing I like specifically is being able to save to a specific folder. It would be nice if there was some I guess if you've got your interfaces in a nested folder, to be able to always go back to that specific folder. Doesn't seem to retain unless I'm missing some default path setting.
It always goes back to your root of your project as its starting point.
Yeah.
Okay.
Yeah. That's the only real comment that I had, but this is pretty sweet. There are a couple of oddities that I have logged with an eye on in terms of adding, and then certain things happen when you delete them, but nothing showstoppering.
There's a question from the forums. Are you going to make your code for this HAL available?
I can do, yes. Okay, so moving on quickly, conscious of time, we may well overrun. So taking this sort of a level further, what we'll do is we'll look at specifically, I guess, the use case that I've used with measurement abstraction, and I guess the one single pitfall that's really bugged me from a general, I guess, being from a software management perspective, managing software itself, and also, I guess, people really, different skill sets is really when you're using pure abstract classes for trying to make your own measurement and hardware abstraction, is that I couldn't really visually top level from the class hierarchy. You can't see what's inheriting from where. I'll show what I mean by that. So you can see here, this is just, again, a real dumbed down, simple example of how I have implemented measurement hardware abstraction before. So we've got our hardware side to the right, which is here, everything inheriting from instrument parent. So again, we're breaking out DMM individual cards. We've also got the DAC type parent, which is, I guess, our interface, abstract class in reality, in that, we've got a DAC type. It could be an analog input, it could be a digital input. With an analog input, you could have voltage, you could have pressure, whatever. The issue here is that looking at that, you don't know what's going on. I know for a fact that a PXI 6221 can do AI voltage, but there's no visual contextualization really to see that AI voltage inherits or is related to that. Where that information would be nested in what I would call a constructor VI, whereby we nest that functionality within its private data, which has got some benefits and drawbacks in itself compared to interfaces. But using interfaces, we can visibly link that inheritance and do it, I guess, the proper way. And you'll see that in the next slide. So I guess benefits for this, it does work. This type of HAL-MAL we have implemented in many different applications, industries, use cases, pure LabVIEW test and Veristand. It's modular. It uses all the OOP principles. It maybe bends a couple of corners every now and again. But there are some drawbacks, as I mentioned. The inheritance is unclear, in my opinion. And if you've got someone that's entry level, just learned about OOP, and you give them this, you're giving them a basic driver to implement, that they're not going to understand what's going on where unless they've had, the intense sort of spiel of this is where things are, this is what happens where. It's not the approach that you would take in other languages, right? So interfaces, as I mentioned at the start, are going to be they are used in other languages. You would probably leverage an interface for a similar sort of use case. And with this implementation, in my opinion, you end up abstracting a level too far. So what I mean by that is you end up having parent classes like MIO and DMM, and then you've got analog input. You've also then got PSU comms type. It can get a bit complicated. We're also, more importantly, we're defining data and operation here. So we're defining that a 6221 can do the voltage measurement, but we're also using that abstract class to action that function as well, which again, there's positives to that, but also negatives if you're looking at it from you're trying to make an interface, if you like. So what we've looked at, what I've looked at translating that into is something that looks a little bit like this. Now, again, this may well not be leveraging 100% best practices. I've tried to simplify and refactor in a way that, going back through documentation that, we are only defining operation rather than data. So you can see we've got the instrument HAL here. You can see we've got defined hierarchy. We've also got the DAC type interfaces, AC voltage, DC current, capacitance, digital output, digital input, voltage output. And it looks messy, but when you look at individual cards and you highlight the connections, you can see exactly what a 6225 can do. You can see what a PSU does. So for me, there is a clear inheritance there. But yeah, you get again. I think you are still open with this example as you are with this example to sort of go a bit too far. Abstract for abstract's sake. But we are abstracting measurement type and hardware. But one thing I will note is that if you are going to do something like this, like the Bloomy document stipulates, you need some kind of like mapping framework, whatever that may be. So again, I'll show you some of the example code that I've put together. There is a test and example as well. Seems to have closed my project, but LabVIEW20 is pretty quick at loading. Look how quick that was. So we'll look at class hierarchy. So again, what we'll do, 6225, highlight connections. Oh wow, amazing. I can see that it can do voltage. I can see it can do capacitance in theory. I can see it can do DC current, DC voltage. Oh, I can also see that it's an MIO card. The visual representation, especially from another developer perspective, is pretty useful. So again, I've got another main VI here. So what you can see is example of how I would use it. It may well be a better way. But in essence, what we've got is we've got our instruments here. So we'll just go with the top example very quickly. So what we've got is we've got the Keithley DMM, we've got the PXI DMM, and we've got a PXI 6225. All inherit from the DC current input interface. So what we're going to be using is we're basically, as you'll see in the shipping example, if you try and wire all those together into an array, it's going to break, or it's not going to break, it's going to go to the nearest class or interface that they all relate to, which is going to be a mismatch, especially if you're getting into larger and larger abstractions. So what we're doing is we're going to more generic class, and we're basically saying go to DC current input interface, and then building an array up, and then executing again functions, open, initializing DC current measurements, reading the current, and then what we're doing halfway through that is we're saying, actually, all these, because I know they are all capable of DC voltage input. So badly using this more specific class, and again, there is a note here, be careful with that, because it can get a bit dangerous, I guess, in a way. We're then going to be looking at DC volt measurement, reading the DC volt measurement, and then closing the session for the whole card. You'll see that I've got DAC type as a call here, as well as I'm losing my words here, as well as the actual interface itself. Again, we are inheriting. I'm not sure if, I guess this is visually how it's meant to be. Stephen, you might be able to confirm, but this is obviously the parent interface, if you like, that the others are inheriting or overriding from. But we get multiple opens, even though there is only one single open override in the actual card itself, for example.
Yeah, that was that looks like a bug that we're replicating that in too many places. I'll take that. I'll take that one under advisement.
Okay, no problem. I didn't know if it was meant to be like that. It makes sense in a way, but anyway.
We were meant to have a reference there to say, hey, it's coming from over there, but it doesn't look like we quite got it right because the feedback's not quite on the nose.
Yeah. Yeah, so we're still overriding. We're just overriding from a parent interface because all instruments in theory need to be opened and closed. There are a couple of exceptions, but yeah. So if we were to run that, what we would get is, again, this wonderful debug VI where we're doing the Keithley stuff, the PXI stuff, the PXI DMM stuff, and then the MIO. So you can see we're opening, configuring, reading voltage. 6225 has not got any kind of configuration functionality behind the scenes, so it executed nothing in essence. The override it executed, but there was no code behind the scenes. So again, there's no parameters. A note here is that there's no parameters passed in here. I would have some kind of mapping framework to do that, whatever your preference is on that. It does just sort of lock it off in a sense visually, but that's one example. Other example we've got here, so this is where I'll sort of touch upon how things change visually. So what you'll see is we've got two power supplies from different families. Here we're actually leveraging traditional OOP dynamic dispatch. You will see that this is the PSU class, it's not the interface, and we can do that because we have a parent class above. If we wanted to utilize the SMU, the source measurement unit, if we went like that, you'll see that it changes to using the voltage output interface. So we could use a more generic class on these classes here, to sort of push it into using the voltage output. But I just wanted to just show that, we are using PSU parent class, and then now we are actually we're calling the interface, but obviously we are overriding to essentially the same functions. So what I'll do is insert element before. What we'll say is 1, and then data operations. Insert element before. We'll say 0.5, for example. So again, we're going to be leveraging the functionality for the override. So you can see I've got some SMU code behind the scenes. I've not wrote anything for 6225 card yet, even though it is capable of voltage output. PSU, again, I've not got the driver layer, so we're going to be calling the debug VI. So hopefully this will work. I've hopefully not given it any bad parameters. Probably just going to change that down to 0.2 just to be sure. So there we go. So the 4130, that's the SMU, and then the CPX and QPX series, that's the power supplies themselves. So we can see we've executed those using the interfaces, no problem at all. Now, how we apply is two more specific interface voltage output necessary. So it would be necessary because if I tried to wire that directly in, this is covered by the shipping example, it breaks because it goes to the first, tries to go to LabVIEW object, and then anything below that it can combine towards. But because the SMU can do current sourcing, for example, but the PSU in theory it probably could, but there's no commonality, so we can't utilize the overrides that we need in the interfaces. So in this instance,
Martin should note that that's not a 2 more specific, that's a 2 more generic, which is a no op at runtime.
Yeah. Yes. That relates to my comment up here as well. So I didn't know if you were talking about the input when you said that then. But yeah, so I'll read that note out. So more specific classes, more specific is used for runtime checks, has significant performance overhead. So more generic is checked at compile and is no op. So yeah, so be careful with that. You'll see in the shipping example, there is one that talks about using those functions in the right way. The joy of interfaces sharing a lot of the commonalities and I guess creation and things like that with classes means that in terms of how we write that in terms of test end code, it's fairly similar in terms of we can pass in an interface or a class. We can still call an interface as a class member call, much like we would with an object-oriented normal class, if you like. You can see I've set a very basic example up here whereby we're getting instruments from our mapping framework. We're initializing the instruments based upon a dynamic array of instruments. We're then applying a stimulus to the unit under test, and then we're basically getting some measurements from it. So digital input output, voltage, reading a load, for example. So if we just run a single pass, I'm calling the interfaces. You can see my debug VI is working. That should be, if you turn that into ASCII, it should say #VIWeek. So that's cool. So you can see my interfaces are actually being called much like they were in the pure LabVIEW example code that I showed. Personally, I can't really think of a use case where I would be putting LabVIEW code and interfaces in a for loop like that, but it nicely shows off the method of using to more generic class things like that. So you can see code executed as you would expect. So what we've got down here is, now the demo is going to go right and it's going to be quick. So we've got a spec change whereby we need to apply a current source from our SMU. So what we need to do is we need to be able to create that functionality. So first of all, what we need to do is, I'll just minimize these. So what we're going to do is we're going to go File, Unload Our Modules. Fantastic. That's great. We'll reload it, don't worry. The only thing is I've got a sticky note right next to me that says, do not unload all modules from test stand, close test stand and reopen it. Anyway, you live and you learn. So we'll recover it. It's fine. It's live. At least you know it's not recorded, right? Oh, it is recorded. Damn. Okay, so it's an output. So what we want to do is we want to create the interface first. So what I'm going to do is right-click, New Interface, and what we're going to call it is Current Source. And what we're going to do is make sure that interface inherits from DAC type parent, and we're going to save it to interfaces, current source. Okay, right. Then what we're going to do is we're going to create a new VR from Dynamic Dispatch template. What we'll do is we will call that current source, set current source, for example, and then we'll set that. I'll quickly do an icon. Okay, so that's the VI that we're using in the interface. Now I want to use the SMU. Okay, so what we want to do is source SMU PXI write, and then what we want to do is, well, actually what we want to do first is we want to make sure that the interface is part of its inheritance. So into inheritance, if I'm going quick, I apologize, I'm conscious of time. So you can see the interfaces that we're inheriting from. What we want to do is we want to use the current source, press OK, OK again, right click, new, VI for override. You can see set current source is there, and you can see we've got it here nicely. So I didn't set that there, did I? So that shows it inherits, right? The arrow's broken. Okay, so that's fixed now. So set current source, we'll just put that there. We will save that. I'm not going to put any functionality behind the scenes, just in the interest of time. But what I'm going to do is in fact, I will, because it's going to bug me otherwise. So what I'm going to do is just very quickly take that. I'm not going to bother with the actual API. Current set to, choose that very quickly. Use that. And into there. And excuse the wide ends.
Just so you measure your time right, you've probably got about 5 minutes before people start really bailing.
Yeah, that's fine. We will be done before then.
Okay.
Thanks for that. All right, we'll load a test them then quickly. So there's a lot of commonality here between how you would set up an abstract class. Really, you know, we're overriding VIs in pretty much the same way. So, and a lot of it carries through here as well. So we'll set that as to normal and set current source here. So what I'm going to do is I'm going to search for the class. We look for interfaces, current source. We're going to use relative path, set current source, and there we go. So what we're going to do is we're going to take the reference, or wherever the reference will be, which should be in that location there, and we'll just say 0.1. And we will do that there. So you can see we're calling the interface. We're not actually calling anything to do with the SMU. It should inherit automatically. So what we will do is we will just run that, and it's going to work. Better work. Okay, so that's our bit stream now. Oh, piece of measure. Okay, ignore that. Ignore that. So what we should see, the important thing, the fact that the other stuff broke, that's fine. 4130 the current was set to 0.1 amps, and then we actually set the output to true. So in theory, that's done exactly what we needed to do. We've basically implemented the interface. We've called the interface set current source. It's overrided into this VI, and it's called our debug VI, which fantastic. The other stuff, possibly the reference still being open, but anyway, we'll not worry about that. But that's how easy it is, and that's how similar it is in terms of LabVIEW classes and interfaces in terms of a test stand perspective. A bit more of a real world example, if you like. It helped me get my head around it. So, a quick summary then. Really, so interfaces are awesome. I really, really do think that. There's a lot of good use cases outside of HAL and MAL for interfaces. I mentioned active framework, abstract messaging, mock objects, things like that. A lot of benefits to them. So modularization, it's a big part of solid OOP principles. You've got visible inheritance, and the interfaces are applicable to many areas, like I've mentioned. There's some pitfalls. So there are elements that I do like about using pure abstract classes. I think there could be some repetition in terms of overriding, but I think the benefit of using interfaces in the real way outweighs that. Documentation, again, for it's a very, very new feature for LabVIEW, so it's going to be a work in progress, right? And hopefully stuff like what I put together and what like Tom and Boring Engineer blog post has put together is going to help people with that. And a style guide as well. Again, I don't know if that's work in progress. What are best practices? You can extrapolate a lot from text-based languages, but we concentrate on LabVIEW, right? We want to know what's correct and what's not. So again, work in progress. I imagine OOP was in a similar position 10 or so years ago, and look where we are now. So if you can play around with them, you've all got access now to LabVIEW Community, so I recommend you get that installed and have a play around. There's plenty of resource and people that are happy to discuss it. And a quick plug, Quick Drop Podcast, you might have heard about it. Hiatus for some time now. There are some old episodes that are on there that I did with a number of people, like Jörg Hampel, guys from GDevCon, Cross, and whole range of different people. So if you've not heard it, go and give it a listen. Hoping to resurrect it sometime soon. But yeah, I guess really any questions? I appreciate we've gone over by a little bit. If you want to jump straight into the Discord chat, or you want to anyone wants to hang around for 10 minutes or so, I'll happily do so. Yeah,
this was well done. Thank you, Jonathan.
No worries. Thanks for the policing the chat.
Yeah, I didn't see anything that was specific to you that was left unanswered. So
cool. Good.
If anybody's got anything, go ahead and ask. I'm going to drop out. Thank you.
No problem. Thanks, Stephen. Yeah, lots of reading, Bob. I'll make sure that the references are put on the Discord chat, and I'll make sure that if they can be put on the LabVIEW wiki page, if they can at all. So a question from Tim. So his takeaway is that you think interfaces are better for a MAL than a HAL. I think they're good for both, but I think personally there's a lot more that you can do better with interfaces with MAL than HAL. I think if I was doing a HAL now, I probably would use interfaces, just from a personal preference, but I would definitely use interfaces for measurement abstraction. But that's my flavor of MAL. There's many different ways to skin a cat, I guess, really. URL with the examples. I'll probably put these on a public Git repo so people can download them, and also make sure that the links are put on the LabVIEW wiki and on the any forum post or anything like that. So. All right, guys, I'm going to close it off now. If there are any further questions or anything that anyone wants to ask later on, there's the Discord channel. You can ask questions on there. All right, thank you very much, everyone. Bye-bye.